Hello, and welcome to Chapter 10, Section 2. This is actually the last section of Chapter 10. Chapter 10 is really short. So today we are still dealing with two samples at a time, and we're still doing hypothesis tests and confidence intervals. Last section we looked at proportions. Today we look at means. So our hypothesis test for today will be called the two-sample t-test because we are dealing with two samples, and then it's a t-test because we don't have population standard deviations. We're going to have two sample standard deviations, and that's when we use the t distribution. And then with our confidence intervals, our name for it is going to be the two-sample t-interval. Same reasoning. All right, so before we begin with our example, important life question to ask you. Do generic brand cookies, chocolate chip cookies, have as many chocolate chips as name brand chocolate chip cookies? This is a very important question. As a person trying to become an adult in life, I'm faking it the whole time, but it's fine. The important questions are, am I getting enough chocolate chips? Duh. I'm also trying to save money because, being a teacher, I don't get paid a lot. But generic brand, I can deal with it as long as there's enough chocolate chips, obviously. So, big question here. In order to figure this out, we're going to get 10 bags of Chips Ahoy cookies, because that's the name brand, and then 10 bags of Great Value cookies. I don't know if you know, they're from Walmart. Meh. And they are randomly selected, because obviously we got to do this right. One cookie was also randomly selected from each of those 10 bags of each brand. And then the number of chocolate chips in the cookie were counted. So broke them all apart, counted the chocolate chips in each one, and this is the data that I got. Is there convincing evidence that there is a difference in the mean number of chocolate chips? Okay, so this is the question we're trying to answer. It's obviously a very important question, so here we go. So because this question is asking us for convincing evidence, obviously we need to do a hypothesis test. So specifically the two-sample t-test, because we have two samples. We were given a sample of chocolate chips with the Chips Ahoy, and then we were given a sample of chocolate chips coming from the Great Value cookies. So these are two different samples because I have two different groups of cookies here. So two samples. A lot of times this is kind of like a question that people tend to have when they come across these problems, because now as we keep adding on different hypothesis tests, the difficulty now is being able to tell what kind of test to use, because we have the one sample, we have the two sample, and if you remember with our means, we also had the matched pairs one. So the matched pairs was where they specifically took like from two different sets of data, like a before and after or something, and then subtracted each of the values within the data set to then make one new data set that was the differences of all of them. Well, here it wouldn't make sense because we aren't just comparing cookie to cookie, we are comparing brand of cookie to another brand of cookie. So as a whole, on average, is the average number of chocolate chips of Chips Ahoy going to be different from the average number from Great Value? Versus before, if you remember back in Chapter 9, we did a problem with the SpongeBob and Sandy Cheeks in the Bargain Mart and the express lane and the regular lane. So that was a matched pairs problem because for each visit that they went to the store, they were comparing the times of the express lane and the regular lane. But because each visit was kind of independent from the next one, then we couldn't kind of look at all of the visits of the regular lane versus all the times of the express lane as a whole, as an average. So that's the difference. We need to make sure we can make that distinction. Okay, so for this problem then, for a two-sample t-test, I wanted to use this example to kind of go through the whole phantom process. So of course, we're going to start out with P for parameters. So here, because we're dealing with means now instead of proportions, we're going to need to define what each of the true means we are looking for. So I just like to use numbers 1 and 2. You can do something like C and G, C for Chips Ahoy, G for Great Value, something like that for your subscript. It doesn't matter as long as it's easy to identify. So we're going to call mu1 the true mean number of chocolate chips. I'm going to abbreviate chocolate chips. So mu1 is going to be the true mean number of chocolate chips in a Chips Ahoy cookie. So then mu2 is going to be the true mean number of chocolate chips in a Great Value cookie. And I tried to look up pictures of the actual cookies. So apparently Great Value. They're called Chippers instead of Chips Ahoy. Not the same name. All right. So we have our parameters stated. This is what we're trying to find. We're trying to figure out like the difference between these two. So making our hypotheses then, for our null hypothesis, we always use the equal sign there. And so remember, our null hypothesis is always stating that there's no difference between the two. So that means if there's no difference, they should be equal to each other. So mu1 equals mu2, or if you want to write it in terms of subtraction, mu1 minus mu2 equals 0. And again, it doesn't matter which way you write it, either is fine. Then our alternative is based off of the question, like that we're trying to find evidence for. Is there convincing evidence that there is a difference in the mean number of chocolate chips? They didn't say anything about one being bigger than the other. They just want to know if there's a difference, because I do want to know, like, is it going to be the same number of chocolate chips, like on average, or is one going to be bigger than the other? I don't care which one's bigger. I just want to know, is there that difference? So if that's the case, we just need to know if they're not going to be equal to each other, because we don't care whether that's greater than or less than. So the other way to write it, we can also say mu1 minus mu2 does not equal 0. So that would be our hypotheses. Our next step is to check for our assumptions/conditions. So remember, we need to check for random samples, and because we have 2 samples now, we need to make sure both of our samples are random. Both of our samples need to be independent, and both of our distributions need to be normal. So in terms of random samples, they did tell us that the bags of cookies themselves were randomly selected, and then the cookies themselves were also randomly selected. So definitely randomly selected there. So I'll just say that it was given. Given, or you could say it was randomly selected. This is our proof. Okay. For independence, we need to make sure both samples are independent. So since our sample size is 10 for each, then that means there should be at least 100 cookies of Chips Ahoy, and there should be 100 cookies, at least 100 cookies for the Great Value, which is definitely true. They make so many cookies. All right, lastly, we need to check for normality. So for normality, we either need for the original distributions of each sample to be normal, or sorry, the original population distribution to be normal, or we need large sample sizes. We have neither one of these so far, because our sample size for each of the Chips Ahoy and the Great Value is only 10. That's not a large sample. There's nothing in the problem about anything being normally distributed, so that's out of the question. Then our only method left is to graph each of these data sets and then see if there's extreme skew or outliers. All right, so I've just finished entering my 2 sets of data into L1 and L2, L1 being Chips Ahoy, L2 being Great Value. So I just want to graph this out real quick, make sure there's no extreme skew or outliers. I'm going to do this by turning on 2 stat plots. I'm just going to use the box plot so that I can check for outliers really quick too. And remember, it's the modified one with the dots to make sure that it'll check for your outliers. So XList would be L1, and then, cool, I got all of that. And then I also want to turn on plot 2. But this time I'm going to graph L2. Okay. I'm going to zoom stat for this. Ooh, there it is. Okay. There was an outlier, and turns out I had typed one of my numbers in wrong in my list. That's fixed now, so there are my graphs. I'm just going to do zoom 9 one more time to kind of adjust the window a little bit. There we go. Okay, so this looks better. Here are my 2 graphs. So remember, the top one was Chips Ahoy, the bottom one was Great Value. So I just want to sketch each of those out, and remember, I need to tell my audience that there's no extreme skew or outliers, but they have to see that graph, otherwise how will they know? All right, next we want to make sure that we name our test. We said already it was going to be a 2-sample t-test, and I always forget, but this is also the spot where I like to put my significance level. I know in all of my other videos I totally forgot to keep writing it, but here we are. Just a little bit late, but here we are. Because they didn't tell us what significance level to use, so technically we get to choose. You're technically supposed to choose before you actually make your conclusion. But, I mean, so here we are. We're going to name our test, also state the significance level. That way we state to people, this is what we're using. All right. So finally, we get to start our calculations with our test statistic and our odds. So our test statistic formula looks like this. To me, it's easier than the proportion one, at least. But we start off by subtracting our sample means together. Because remember, we're looking for like the difference between the two averages to see if there's a difference between them. So we're going to subtract to find that difference, minus the population means subtracted. And this number, again, is just like the proportion ones. It's usually 0. Then we're going to divide by big square root. So here, S1 stands for the standard deviation of sample 1. Square it, so like the variance, divided by the sample size of the first sample. Plus, and then we're going to do the same thing for the second sample, the standard deviation of the second sample, square it, divided by the sample size. All right, so there's quite a few things to calculate here since we have 2 data sets. So in our calculator, I've already typed in all my data because of, I put all the Chips Ahoy in L1, Great Value in L2. So at this point, I'm just going to go over, remember a little shortcut with their tests in the calculator? I'm going to go over to tests. This is going to be a 2-sample t-test. So again, make sure you choose the right one because a lot of them sound familiar or sound similar. And then here, because they give you 2 options for your input, you can either choose data where we typed in our own data into L1, L2, or if you scroll over to the right to stats and hit enter, you can actually input your own. So in the problem, if you're given a sample mean and a standard deviation and so on, then you can just enter it all here. But we actually have data, so I'm going to choose data. And then my list 1 is in L1, my list 2 is in L2. You can actually change these into like L3, L4, whatever you want, but our stuff is in L1 and L2. Frequency you're going to leave as 1. Don't change that. And then we get to choose for our hypotheses. Did we do does not equal, less than, or greater than? And we had an alternative hypothesis of does not equal because we were looking for, is there a difference? Pooled. This part, we always choose no. No pooling. The reason is pooling is like a slightly different formula, and it's only used when you have the same variance, same standard deviation for your 2 samples, and that rarely occurs. And on the AP test, like just never occurs. So we never pool. If you do pool, you're only allowed when the 2 standard deviations are exactly the same, and because it's so rare, we just don't do it. Also, if you just remember to never pool, it actually comes out with accurate answers, even if you did have equal variances, equal standard deviations. Even if you don't pool, it's still accurate. So really, we don't need it ever. So just remember, never pool. So now we go down to calculate, hit enter, and then it'll do everything for us. So first of all, it already calculated our test statistic T for us. Because it's a t-test, it's a t-score, so we get a t-score of negative 0.788. And then a p-value, remember the p-value is right underneath, so that's our odds of 0.444 something. Also, take a look at our degrees of freedom here. We've got, what, decimals, 13.14, what the heck is this? So when there are 2 samples, the degrees of freedom formula is much more complicated. Before we were just doing degrees of freedom when there was 1 sample of just n-1, because that was simple. There's actually a much more accurate formula, and you don't need to know the formula. I'm not here to complicate the formula for you, so no formula, just use the calculator number, have your calculator do it for you. So this is our degrees of freedom. Let's say, for whatever reason on the AP test, your calculator busts and you run out of batteries, you can't do this using the calculator. In that case, the more conservative estimate is to take the smaller sample size and then subtract 1. So kind of like our degrees of freedom equals n minus 1 formula, but always with a smaller sample size that you have. In our problem, our two sample sizes were exactly the same. We had 10 as our sample size for both. So you would just do 10 minus 1, which is 9. If your two sample sizes were different, you would choose the smaller n and subtract 1 from it to find your degrees of freedom. But if your calculator works, you don't need to, and this is much more accurate this way anyways. So in terms of showing work for our test statistic, you don't have to write out the formula, but you want the numbers plugged in. So I'm just going to write out t equals, and the calculator told me 18.4 was my x1 bar, and 19.4 was my x2 bar. So those get subtracted. And then our mu1 minus mu2 should be 0 over. And then when you scroll down, you should be able to see all your standard deviation numbers, and also n, in case you didn't know your sample size. All right, so I've plugged everything in, but we're just going to take the number that our calculator gave us for our test statistic, negative 0.788. Okay, once we've got that, I'm also going to list out under the test statistic what my degrees of freedom was, because there are two ways to find this. We definitely want to tell people, like, when I find the odds, this is the degrees of freedom that I'm using, and this is where I got it from, either the calc or the table. So if you're using the table way because your calculator didn't work or whatever, and you're using the smaller n minus 1, then you would just say, like, table or conservative method if you want to be real fancy about it. But just make sure you list out your degrees of freedom. And then listing out my odds, the calculator told me the p-value was 0.4445, so I'm just writing it out with t being less than our t-score of negative 0.788, that was from our test statistic, equals the p-value. Cool. Finally, we make a decision, and it's the same format that we've been doing. So our p-value of 0.445 versus our significance level we stated earlier was 0.01. So our p-value is definitely greater. So we fail to reject. There is not convincing evidence that there's a difference in the mean number of chocolate chips between the Chips Ahoy and Great Value brands. One thing I want to point out here is in your conclusion, make sure you're using the word mean, because we are dealing with true means here. So the difference in the mean number is basically saying, like, we're taking the averages of each of our populations and subtracting them, and that difference in the means is what we're looking for and what we're trying to draw conclusions about. So make sure we're not just talking about the difference in the number of chocolate chips, it's the difference in the mean number of chocolate chips, because that's the whole point of a hypothesis test. Well, all right, so based on our little hypothesis test here, we basically found that we couldn't reject HO. So if there's not evidence that, or there's not convincing evidence that there's a difference in the mean number of chocolate chips, then that means when we buy generic brands like Great Value, we're getting more bang for our buck. We've got more chocolate chips for less money. Fantastic. Life's questions being answered. Ugh, so good. Okay, so lastly, I want to talk about the confidence interval then. So the confidence interval formula is pretty similar. Here's the formula. The panic process is pretty much the same as our phantom process with the assumptions and the conditions. So we said the name was going to be the two-sample t interval. In the calculator, when you do stat and then go over to tests, you're looking for the two-sample t interval, which would be down here. So again, make sure it matches the name of your interval. That's kind of easy to remember. Alrighty, that's it for this section. Thanks for watching. Don't forget to like and subscribe. Bye!